Oh my gosh. I'm not contented with my whiteboard, right? So I can explain only less, not too much. Okay. Oh my gosh, there's a reflection. Oh, gleaming. Oh, what's happening for the gleaming? Okay. So it's here. Oh my gosh. You can see me now vividly, Charles. Okay? Now I need to intensify my voice. Where is my microphone? It's here.
The Bluetooth device is ready to pair.
Hello guys. Good morning, good afternoon, good
The
evening.
Bluetooth device is connected successfully.
Good morning, good afternoon, good evening. Let's go back to our main topic on about heat problems. Okay, so there are a lot of ways how to solve this. Could you use also the specific formulas? Okay, and the dimensional analysis through conversion factors also, and then by illustration, schematic diagram with simultaneous also remembering of the basic concepts of the basic equations and formulas to be used with regards to heat. Okay, things like that, or we can say also enthalpy of reactions. Okay, get the point, or heat content or heat summation, like that, whatever. Okay, so there's heat, H-E-A-T, or diba. Okay, our problem starts with 100 gram of iron metal. Okay, iron. Remembering iron. Iron is the raw material for rusting process and corrosion process. So we have Fe positive 2, Fe positive 3. Iron 2 and iron 3. The charges are 2, right? Because iron belongs to the transition metals in the periodic table. The atomic weight of iron is 55.85 grams per mole. Okay? And this is highly electropositive. Okay? Oh, yes. Okay, and naturally occurring element. Okay, it's not really chemically combined or whatever. It's really found in nature. Okay, so at 95 degrees Celsius was placed in a 200 grams of water at 25 degrees Celsius. What is the final temperature of the mixture? It talks about temperature changes, right? Not the phase changes. You get the point. So let's go now to our solution. But before anything else, what's being asked is the final temperature, right? So let's denote that as TF. Okay, required. When we mean of required, this is what is being asked. So TF meaning final temperature. Okay, like that. Okay, required. Next, data or given, like that. What are the given in the problem? We have the mass of Fe. Okay, mass of, if E is equal to iron, right? 100 grams. Okay. Since our topic for today or this moment in time is all about heat or heat amount energy, then our specific heat capacity is very important. Okay, see, specific heat capacity. Let's see. Sometimes we will denote that also as CP or C. It depends, but how you understand matters the most. Okay, so let's just put this as CP because usually we put CP in our equation. Q is equals to MCP D delta T or QMCP delta change of temperature. So CP, okay? So this is not computer, this is not also cell phone, but specific heat capacity. Okay, we have 0.45, okay, gram degrees Celsius. So if we mean specific heat capacity, then there will be Celsius here at the denominator. You get the point? But if you will simply say heat capacity without the term specific, then there's no necessarily putting the Celsius or whatever, things like that. You got the points, joules. Okay, this is joules. Okay, because this is specific heat. Okay, joules. Okay, any questions so far? Okay, I'm very, very excited to discuss, that's why. Okay, so you remember that joules is in the numerator, okay, and gram degree Celsius is in the bottom. So meaning to say, the amount of energy or heat energy required to raise 1 gram of a substance to 1 degree Celsius. That is our specific heat capacity. Okay, and our heat capacity, okay, is don't involve the grams, only the joules per degree Celsius. That's the difference between specific heat capacity and heat capacity. So when you mean of specific heat only without the word capacity, then it could mean this one. Okay, so it sounds confusing sometimes, but if you are really observant on the conversion and the cancellation of the units, it's not an issue for you. But you know, sometimes it's really ambiguous, especially if we are not really fast learners in science, especially me. I'm not really that superior in understanding. So it needs for me to draw back the basic concepts before I understand very well. Okay? Okay. Now, we have here at 95 degrees Celsius, this is the initial temperature of your iron, right? So, TIFE, 95 degrees Celsius. You don't have to convert the degree Celsius into another units of temperature because it's compatible with the unit of your specific heat capacity. And it's easy to cancel that out somewhere along the way of your solution, okay? Or your computation or calculation. Okay. Okay, agree? Now, the method here in solving the solution, okay, so your basic formula here is Q is equals to MCP delta capital T. Okay, it doesn't matter if it is Kelvin, okay, because this capital T here is in Celsius. Unlike the ideal gas law, when you mean of capital T, that's always Kelvin, huh? Here, it doesn't matter whether Celsius, Fahrenheit, Röntgen. It depends on the units mentioned in the problems. Okay, but in the ideal gas law, you need to convert really that to Kelvin in order to substitute in the general gas equation conceptualized by Mr. Clapeyron. Okay, in our physical chemistry or thermodynamics. Okay, now we have here, this is our general equation. Okay, in our problems, we have two substances, pure substances, because iron, as I said a while ago, it is naturally produced in the Earth's crust as a naturally occurring metal. Okay, natural. And also water is natural by nature. So these are all pure substances. Okay, both water and iron. You get the point? Things like that. So you need to denote subscript here indicating the iron and the water. Okay, so our illustration to understand further. Illustration, drawing, schematic diagram, flow chart, or whatever. Okay, or sketch. Okay, so I have here, okay, the container is not mentioned whether it is a beaker, flask, a funnel, or whatever. Get the point? It's general. So let's assume we have the graduated cylinder here. Okay, inside the laboratory. Okay, things like that. Okay, graduated cylinder. Okay, with markings like that. The readings, for example, only for the purpose of discussion. Okay, things like that. Okay, was placed in a 200 grams of water. So there's a water inside the graduated cylinder. Okay, amounting to 200 grams. Okay, like that. And at 25 degrees Celsius. Okay, like that. So this is the temperature of the water. So we will say this as, okay, initial temperature of water. Okay, and this is the mass of water. Okay, to the point. Now, your problem, you don't have the specific heat capacity for water. Okay, this is where, the logic requirement for every student to memorize the specific heat capacity and heat capacity of water. You get the point? Because some problems no mention of the specific heat capacity at, standard ambient temperature, okay, and pressure. Before going further, I may explain also between STP and SATP. Okay, when I was in high school, I always confused about this. Okay, what's really the standard temperature of this water? In order I can have the density of 0.999838 rounded off to 1. Actually, it's not really a perfect 1. It has been rounded off to 1 only at standard temperature. Now, here in water, our standard temperature is 25 degrees Celsius, 0 degrees Celsius, or 4 degrees Celsius. This is really the issues we face. Okay. Now, since you memorize only that you believe that it's already 1 because our teachers are always using 1 as the standard density of water, then at what temperature for that? Okay, we know that the standard pressure is always 1 atmosphere. So it could be the temperature looks like there's ambiguity. If it is A, 20 degrees Celsius, B, 25 degrees Celsius, C, 4 degrees Celsius, D, 0 degrees Celsius, A, none of the above. For example, if we treat this very simple question in a board examination, and I will ask, okay, what is the standard temperature of water when the density is equal to 1 grams per ml? What will be your temperature? There's a lot. A, 20 degrees Celsius, 25 degrees Celsius, 4 degrees Celsius, 0 degrees Celsius. Now, let's go one by one. A. This is the minimum standard temperature at room temperature of most substances. Okay, minimum. Okay, now B. This is the standard temperature at maximum level at ambient temperature. Ambient. Okay, now C is the special temperature original from water to create certain changes of your density. Okay, D, 0 degrees Celsius is the standard temperature pressure, STP. Okay, pressure is 1 atmosphere, temperature is 0 degrees Celsius. But are you sure this is the temperature we use so that we can get the 1 gram per ml that we always use every time until our graduation, during the board examination, or even in our workplace? Right? We memorize exactly 1 gram per ml, 1 gram per ml. Digit tama sa'yo. But what is the temperature for that? Why we obtain that density? And you need to ask yourself, because this is not magic. Once you get that, there must be a corresponding temperature and pressure. Okay? Your mind at least will be inquisitive for that particular question that may arise. You get the point? Okay, so when I was in high school, I always use 25 degrees Celsius because according to the textbooks, this is the standard temperature at ambient temperature, in which this is SATP. Standard ambient temperature and pressure is not equal to STP, standard temperature and pressure. What's the difference? The dropping of the capital A of the acronym and the abbreviation would mean not exactly the same, the definition. When you mean of STP, standard temperature pressure. Okay, SATP, standard ambient temperature pressure. Okay, so which among these standard conditions I will use? But it should be STP or SATP in order for us to get the 1 gram per ml density of water at standard condition. Because both are standard conditions. Right? By experimentation of our previous chemists in the past. You get the point? So what? What temperature is that? Okay, now I started to research a lot when I graduate in high school. Then after winning the chemistry quiz bowl, and then I love science too much like that. I research even though in the vacation, no classes, I still study in home. You get the point? Even though there's no classes, only vacation, scanning books like that. Okay, like that, things like that. Okay, now I found out, okay, that it is really 4 degrees Celsius when we get that 1 grams per ml. Now it deviates because 4 degrees Celsius, this is not SATP and this is not STP also. Okay, as opposed by many students, okay, or many engineers that we think that 1 gram per ml water is the standard condition. Do you think 4 degrees Celsius is the standard condition? This is done experimentally. That at 4 degrees Celsius, the water will achieve a density of 1 gram per ml as our standards to be used. Now, it deviates the rule of STP and SATP because most of the substances will follow SATP, standard ambient temperature pressure at 25 degrees Celsius. You get the point? So, ambient temperature of the air. You get the point? So, our answer here is letter C. 4 degrees Celsius, so that we can achieve a density of 1 gram per ml, which is exactly equal to 0.999838, rounded off to 1. That's the point. Things like that. Any questions so far? Nothing, right? Okay. This is for illustration. Now we dip the iron. Okay? So, iron mass have. Okay? CP have initial final temperature of iron, initial lang siya, no? Of iron have water, initial have mass have okay? What's the specificity of water? At SATP. Okay, it is 4.18 joules, okay, gram degrees Celsius. Now, SATP, I'm saying STP. STP usually applied in ideal gas law or Dalton's law at 0 degrees Celsius and 1 atmosphere. The volume of 1 mole of a gas will occupy 22.4 liter. Things like that. That's the standard of Dalton's law of partial pressure. Okay, if you can remember the theory, right? Things like that. Okay. That's very clear. Okay, so we have now the CP, the initial temperature, and the mass of the water, and we have also the mass and the CP of iron initial. So almost perfect. So what left is our final temperature is what being asked. So we need to solve this one. Now, you dip the iron here inside the graduated cylinder. Now, in this concept, we need to remember the first law, the zeroth law of thermodynamics. As you can remember, we have the 3 laws of, the thermodynamics, right? Okay, the law of conservation of energy, the zeroth law, the law of entropy, like that. First law, second law, third law, like that. Okay, this is zeroth law. What do you mean by zeroth law in thermodynamics? Okay, this is that zeroth law. The zeroth law means that if you try to mix the substances over the other, they will have the same temperature in equilibrium during transferring and mixing. Okay, so they will have established the same equilibrium temperature. So the temperature of the iron will also be the temperature of the water at final state, like that. But initially, you didn't have the same. Okay, now, so in thermodynamics, we will also remember the heat released and heat absorbed in zeroth law. So, okay, how can we do this? So, heat released, okay, is equal to heat absorbed. Okay, like that. You get the point, mga palangga kong hitad. Okay. Heat release is equals to heat absorbed. Okay. For example of heat release, okay, so we have the atmosphere. our atmosphere is, driven by the sunlight, radiant heat of the sun. So that, for example, that is our system. It will release heat to the environment, to the planet Earth. Now, the planet Earth or the environment or the land in which people live will absorb the heat coming from the sun, right? So we will have a positive heat, things like that. And the system which is the sunlight, okay, in the atmosphere like that, we have released, meaning to say negative heat, because they release the heat going to the people in the land. It's the same principle here. You get the point? So heat release to the water or the metal. Okay. Of course, when you dip the iron will absorb the heat. So iron will be Q iron will be positive heat absorbed. Now your Q water will be releasing the heat to be absorbed by the water. So heat release negative Q water. Negative Q water. And this is now your equilibrium temperature of your zero flow. Okay, the heat release of the water is equal to the heat absorbed of the iron because you mix and combine them in one container. They will share the same heat and temperature in a final state. Any questions so far? Nothing, right? Now, either we go individually in the computation of negative heat of the water, heat release, and also the iron, or
The
either
Bluetooth device is ready to pair.
we will substitute them all in one equation. It's up to you how you are convenient and comfortable in doing so your calculation. You get the point? But in here, it looks like I don't have space anymore, right? Because my whiteboard is so very cute. It's not wide. So I will not be satisfied in comprehensive discussion. I need a very wide dimensional, whiteboard. Okay? But I don't have, sorry. Okay, things like that, no? So let's erase the problem. Either way, we already noted that one. Right? Things like that. Okay. Now when you discuss, please write legibly. Your handwriting must be clear to the students and to the pupils so that they can understand also. Okay? Your penmanship must be good. Okay? Things like that. Or readable or visible. Okay. Now, negative Q heat. Okay. Carry the sign. Negative Q. Mass of water, insipidity, mass of water, 200 grams. Okay? Like that. Carry all the units so that it's easy to cancel. Specific heat capacity of water, we have 4.18. So, 4.18 joules, gram, degrees Celsius. Okay. Change in temperature of the water. Okay. So, the final temperature is missing for both because this is a mixture. So, T, F, water, because we start with water, minus initial temperature of water. It's mentioned or not? It's mentioned, right? 25 degrees Celsius. Okay. Is equal to the heat absorbed of iron. Okay. So, positive Q. So, mass of iron here, 100 grams. Okay, specific capacity of iron, 0.45, okay, joules, gram, degrees Celsius. Now, final temperature of your iron, in which you do know also, so we have EF, if E, minus initial temperature of your iron, okay, which is 95 degrees Celsius, right? When we see Celsius, that's also the same with centigrade, huh? Okay, centigrade or Celsius are just the same. Okay, get the point. Okay, now perform the mathematical operation, linear algebraic equation without exponent. Okay, Things like that. So this is distribution multiplication in math. Okay. 200 times 4.18 times TFH2O. Okay, so it will be 200 times 4.18 is equal to 836 TF. Okay, 836 TFH2O negative because there's a sign negative here. Okay. Now, distribution multiplication. Negative times negative, your answer will be positive. Okay. Now, since this one 836 is the product of the two, then you simply times this value. Okay, you got the point? Okay, 836 times 25. Okay, 20,900. Okay, 20,900. Take note of the, units. Okay, so it's gonna be, okay, degrees Celsius. Okay, joules, gram, degrees Celsius, cancel, right? Okay, and this one. Okay, this one, see, grams, cancel. So joules, degrees Celsius, this one. Okay, joules, ganon, di ba? Okay, joules, okay, degree Celsius, mga palangga. Okay, got the point? Ganon. Okay, now you have here the same story multiplied here like that. Okay, how much is that? Okay. Okay, pila mo na siya mga palangga. Okay, so akong tanawon kung pila din na siya, no? Okay. Wait. Okay. Joules per gram na siya mga palangga, no? Okay. Okay, then cancel ang grams. Joules ang mahabilin. Okay, di ba? Oh, Celsius times, okay, 1 over Celsius, cancel Celsius. Okay, grams times joules over gram, cancels grams. So, joules ang mahabilin dari ari ng unit sa TFIH2O. So, joules. Beside. Here also joules, because the same units are being involved. So, joules. So, joules, like that, right? Okay, ganon. Okay, mawala man siya ang Celsius. Or, pwede na sa Japon, later on, you will carry over the units. Okay, so 100 times 0.45. Okay, pila siya, no? Okay, 100 times 0.45 is equals to 45 TFE. 45 TFE. Okay, minus 100 times 95 because this is not negative. Okay, you get the point. So 100 times 95. Okay. 9,500, diba guys? Diba? Okay. Okay, ayaw naman siya. Okay. So 9,500. So you should be careful na in the substitution. Okay, things like that. Now, check your variables if you can directly add, you can directly subtract, or whatever. Okay, here, the one have variables are the TFH2O and the TF iron. Now, TFE iron and TFH2O are the same variable because they will share the same final temperature when you mix them in a graduated cylinder. So you can have that as TF by all or TF with a mixture. Okay, so add this two because the same. You can add if the same variables in math. Again, in math, you can add if they have the same variables. Okay, things like that. Okay, now you can transpose this. Okay, TFPE to the left, it will become negative. So, negative 836 TFH2O. Okay, minus, okay, 45 TFFE is equals to, this is negative. 900, negative 9,500. Then this one, This is positive, it will become negative if it transposes to the right. That's the rule of math. Right? It will become negative 20,900. Okay. Now, you can subtract directly the 833 and 45. Negative 833 minus 45. It's negative. Okay, because the same sign. So 833 plus 45 is equals to negative 878. Okay, negative 878. So I will say TF mixture, okay, is equal to negative plus negative or negative also. Okay, 9,500. Okay, 9,500 plus 2,900. Okay, guys. Diba? Okay, is equals to 30,400. Okay, now in this manner, you have the same sign, negative left, negative right, cancel the signs immediately. Okay, then TF mixture will be equal to 30,400 divided by 878. So this is your final temperature of your mixture, both, because you mix the two. They will share the same final temperature by common sense, right? Okay, so 30,400 divided by 878 is equals to 34.62 is your final temperature. Okay? 34.62 degree Celsius. Now, if this answer will not be found in your choices in your MCQ, then you need to rework the substitution. Maybe you misplaced that substitution. Instead of water, you put that in the iron like that. Okay? You get the point? Because usually the error here is gonna be like that. Okay. So let's check review. Okay. For the water, 200, check. For with 18, check. 25, check. Okay. Iron, 100, check. CP, check. 95, check. Right? So it's okay. You get the point? So perfect. Things like that. Okay? Now, if you don't want this heat release is equals to heat absorb, if you don't want really that one, then you can also employ the other one. Okay? Do not put the negative sign here first in the understanding, but somewhere along the way, still the same again, substitute, and then you can obtain, let's say, negative. Okay, things like that. And then if there's no negative specificate, for example, by theory. So that the answer also positive specificate, because guys, specific heat capacity and specific heat capacity is always positive. Okay, you get the point. It's not negative because of the definition. The amount of heat energy to raise the temperature. How can you raise the temperature if it is very cold? You get the point? So this is the concept of specific heat capacity. But for heat capacity, okay, there's no issue. There's negative because it's only stating the phase change for that particular heat capacity or joules per gram. There's no temperature like the whatever, things like that. But if there is temperature, problem. Okay, like that. You get the point? So, specific again. Specific heat capacity is always positive. Okay, things like that. But not all heat capacity are always positive. Okay, things like that. Am I correct? Correct me if I'm wrong. Diba? Because the definition of heat capacity is, the change in phase from original phase to another phase. Things like that, okay? A particular 1 gram of a substance like that. Okay? So this is our answer. 34.6 degrees Celsius. Okay. Our final temperature when you combine the iron and the water. Okay. Any questions so far? Nothing, right? Okay. So this kind of problem, it looks like very physical. It doesn't involve chemical reactions, right? What if you will be given, for example, a unique equations For example, sodium chloride will be dissolved on water, and then the initial temperature, I love to create kasi my own problem. So when I was in high school and college, I would love to create my own question. And I will be the one to solve like that. So though I study the books, but sometimes I want really to measure my brain if I can also make a question by myself without referring the books. This is very good technique in studying, guys. You will not always depending the problems in the books. Okay, the way how it is being solved, it's okay. Okay, but you know, sometimes you need to create your own to measure really your understanding. You get the point? I'll try to mix up like that so if I can still solve like that. Okay, so for example, so kasi what I really learned, guys, is to become an engineer is to be observant, to be imaginative, to be inventive and creative. Things like that. You have to voice out things like that. Okay, you need to be dynamic. Okay, you need to have logical and comprehension, reasoning ability. And lastly, critical thinking. Okay, can help solve problem solving in a complexity. Okay, these are really the qualities of engineers. You get the point? But if you don't really you don't have a wild imagination, something that is not really good for engineers because you know observations like that, inference, hypothesis. Okay, then you need to correlate that all by having the data analysis through experimental data results like that in a laboratory, whatever, or let's say sampling, data sampling, or you will be able also to do the surveys of the samples and then you collect that later on. Things like this, okay? The applicability or the application, okay? Things like that. Ganon. Okay. So for example, say, sodium chloride in reaction to water is a brine solution, right? You still remember a reaction of water and salt is called a brine solution. If it is highly concentrated. If it is not highly concentrated, it's just a saline solution. So we need to back up with various theories so that we can have good scores in the theories questions in the board examination or whatever examinations that you'll be able to face in terms of sciences because there's always a lot of theoretical questions that doesn't involve numbers all the time. You get the point? Things like that. Okay, saline solution, it's gonna be 10 grams of, let's say, solute and 0.9% of your entire solution. That's your saline solution. Very concentrated solution of sodium chloride that is brine solution. Okay, so you mean to say, you should be careful when this question arrives in the examination. What do you call a combination of water and salt at a highly concentrated solute? Your answer will be brine, not saline. You get the point? Sometimes it will confuse you sometimes a little bit in the choices. A, B, C, D, E, none of the above. Like that. All of the above. Things like that. To the extent also that there's answer. And you will answer none of the above. Okay, but the and also some above. Especially, what are the factors affecting solubility of different solutions and concentrations? A, nature of solute and solvent. B, temperature. C, pressure. D, catalyst. Okay, things like that. So, of course, all of the above. You get the point? Things like that. Okay, now, for example, if I have here, normally guys, in chemical reactions, to obtain the enthalpy of the reaction or the heat of the reaction. Guys, the reaction here, guys, means chemical reaction. We don't put the word chemical already because it's understood. You get the point? So, heat of reaction. Okay, enthalpy of reaction, meaning enthalpy of chemical reaction, heat of chemical reaction. Now, if there are two, you refer, so that will be the enthalpy of change of the reaction or the enthalpy of change of the chemical reaction, the enthalpy of change, not just change, the heat change of chemical reaction or the heat change, the delta it change, delta kasi because change of chemical reaction. We drop the chemical only, just like also in kinetics, right? Chemical reaction engineering, chemical kinetics. You will say, what is the rate low? Rate low. You get the point? Actually, that is chemical reaction rate low. We drop the chemical reaction because it's obviously a chemical reaction. You get the point? That determines how fast and slow our chemical reaction really is in kinetics, the study of kinetics or chemical reaction engineering. Okay? Things like that. You get the point? Okay. Now, for example, if I have sodium chloride plus water. Okay, let's review a little bit with the basic of chemistry. Then water is a polar molecule. Okay, polar molecule, meaning a lot of unpaired electrons. So meaning to say, this is highly polar, meaning there's a strong intermolecular forces. Okay, strong intermolecular forces. Okay, in the water. That's why it is highly conductive to electricity in order for the electrons to be stabilized. Okay, now we have here sodium chloride. Okay, sodium chloride is an ionic compound, neutral ionic compound, and if it dissociates to the water, it will become completely ionized, which is a strong electrolyte. Things like that, and it will give sodium positive plus chloride negative, things like that. And to the point, that is our ionic equation. But in here, we need to deal the chemical reactions completely. Okay, so we have here, so predicting the products. Okay, in your chemistry high school, intermediate high school, you need to study all the behavior, what's really the products upon reacting these two compounds. So that when you go to first year college, second year college, it's very easy. You get the point? Even, I'm arrogant, even though sometimes you don't study anymore, because you know, it's very easy to do the chemical reactions. This is my favorite talaga, the chemical reactions. You get the point? Okay. Okay, so sodium chloride plus water, this is really a hydrolysis reaction. Hydrolysis in chemistry, the reaction of a salt to water to produce acid and a base. So, expected, our product will be acid by theory and a base here. If you try to reverse the chemical reaction, it's going to be neutralization reaction. The reaction of acid and a base to produce salt and water. But your salt, it's not limited only to sodium chloride. It could be barium chloride. Okay, it could be magnesium chloride, strontium chloride, strontium hydroxide. Okay, the OH and the chloride. Okay, so OH, basicity, chlorides, acidity, things like that. Okay, got the point? Okay, or this is gonna be the HCl and this is gonna be the sodium hydroxide. Okay, got the point? So we will just use this because, you know, as an example, because most of the books are always using sodium chloride also. Okay, because this is a strong electrolyte. Okay, things like that. And this is really the electrolytes happening inside our body. Okay, it's really sodium chloride and water. This is a reality example. This is not hypothetical. You get the point? The moment we eat the food and the tastes are a little bit of sour, sweet and sour, okay, because we love it too much with salts, like that, even though less salts, then the salts there will really react to water to produce acid and the base inside our body to undergo different synthesis reaction to have a good metabolism. Why? Because this aids faster digestion if we have an adequate level of our digestive acid, okay, and our pancreatic juice, mainly the HCl. Okay, that's why in the question of chemistry, what is the acid found in small and larger intestine? A, HCl, B, KCl, B, okay, alam na. Okay, that's hydrochloric acid. Okay, as simple as that in our body, inside our body. Okay, things like that. So we have here, okay, HCl acid plus sodium hydroxide. Okay, you get that point. The only difference of hydroxide as a base and alcohol, because alcohol is paired with an alkyl group. Do you mean the alkyl group in organic chemistry? Meaning carbon atoms plus hydrogen atoms attached with the hydroxyl group or the hydroxide OH. Here, in organic chemistry, it will be attached not on the alkyl group with carbon. It will be attached to the elements, whether non-metal or metal. Okay, because I can also have iron hydroxide. Okay, you get the point. I can also have, let's say, copper hydroxide or cuprous hydroxide, cupric hydroxide instead of sodium. You get the point. As in organic chemistry, there's no carbon-carbon chuba-chucho. When you pair that in the OH, that's a base. But in organic chemistry, when you pair that with OH, usually are alcohols. You get the point? Things like that. Alcohol family, ethyl alcohol, methanol, isopropyl alcohol, propanol, butanol, like that. You get the point? Butanol, butyl alcohol, ethyl alcohol, ethanol, propanol, propyl alcohol. Things like that. Octanol, okay, is octyl alcohol. Okay, nonanol is nonyl alcohol. Okay. So there's a lot. Until 12. Dudinol. Dudinol is dodecyl alcohol. Okay, an alcohol that have 12 atoms of carbon. Very large group of alcohol. Okay, get the point. But the maximum alcohol, but not functioning as an alcohol, is the cholesterol. Because it ends also with OL. You get the point? It's all ends in OL are alcohol. Exemption is a cholesterol. Because cholesterol would not mainly function as an alcohol. Okay? It functions as a lipid family that will speed up the carbohydrate reaction, protein, like the macromolecules inside our body. Okay, again, if it ends with OL, that's automatically by default an alcohol. Okay, but except for cholesterol. You get the point? Things like that. Okay, so muna siya atong i-balance mo siya. Okay, balance the chemical reactions, and after that, bingo. I will say, sodium chloride and water are being combined at 20 degrees Celsius. Diba? Okay, calculate the enthalpy change of reaction. Okay, change meaning the heat of reaction of the product minus the heat reaction of the reactant. Okay, now, it depends na if it's in terms of mole, in terms of gram, if you can subtract directly or not. This is the, the most usual mistakes because we cannot directly subtract. Okay, you need to convert muna. Okay, get the point? Now, we have the formula here. In our chemical reactions, we'll still follow the, the temperature change because there's a temperature, I said 25 degrees Celsius, Baden, 25 degrees, 30 degrees Celsius after. So we will use the QMCPDT also. But you see, QRXN, heat of reaction. Is equals to MCP delta T of your product minus your MCP delta T of your reactant. Okay, so this is your Q reaction. Okay, in terms of temperature changes. Okay, now in your heat of reaction, enthalpy change of reaction, HRXN. When you say capital H, guys, they are all heat, guys. But this HRXN mean phase changes only. There's no temperature changes involved. Okay? So this is the gray area that the students must learn. If you take thermodynamics and physical chemistry, physics and chemistry, you need to learn really what is capital H and what is capital Q, because capital H, it's all about heat of fusion, heat of vaporization, heat of sublimation, heat of condensation. There's a lot of something like that, and you will add only latent, understood to be equal. Okay, you should memorize everything about that, so that if there's a problem solving with regards to that, then it's easy for you to solve. With the point, it says, delta H reaction, meaning enthalpy change of reaction or heat of reaction. Basta capital H. Okay, things like that. So it will become the number of moles, o diba? Okay, kani siya. Okay, the number of moles times the delta heat of vaporization and times delta heat of fusion, okay, and delta heat of sublimation and delta heat of, okay, condensation and delta heat of, let's say, deposition and delta heat, all phase changes. Okay, things like that. So these values, fusion, vaporization, like that, is always given standard. Okay, at 25 degrees Celsius, meaning at SATP, meaning standard ambient temperature and pressure of air is our basis of our calculation, not the 0 degrees Celsius, the same as the PVNRT, and not also the 4 degrees Celsius, the same in density of the water, the standard. You get the point? Things that you need to know how to draw the line with saying, the standard for this is like this, like this, like this. It's not always all the time 25 degrees Celsius. Na automatic na yun, no, it's not. Okay, get the point? Okay, sometimes the problem solving also, at room temperature, ammonia behave, like blah blah blah, then the temperature is not given. What is the room temperature? This again theory. Room temperature is normally 20 degrees Celsius. 25 is ambient. Okay, so from 20 to 25, this is the standard temperature, the range. Okay, so usually standard temperature, SATP will be used 25. But sometimes again the problem solving only mentioning at room temperature. So room temperature will start in the minimum 20 degrees Celsius, not in the maximum. Okay. Anyway, you can see that in the choices. What's the correct answer, and that will be your best answer. Okay, get the point? I'm just teaching you what is room temperature, ambient temperature, like that. Chupa-chucho. Okay, get the point? Things like that. Okay. Ganon, no? Diba? Okay. Since you have this already, so you will say QRXN is equals to NHVAP, like that. Okay, you get the point? Things like that. Mga palangga, no? Okay, muna siya yung metabo. Okay, di ba? HRXN. Okay, equal ka sa QRXN. Then you'll say QRXN is equals to NHVAP, NH fusion, NH sublimation, like that. Okay? You equate that directly because as I told you, the small q and the capital H are just only heat content. Okay? So it's logical that you need to equate the temperature changes and the phase changes. You get the point? Because that's all heat. Okay, but you need to take note every time the compatibility of the units for cancellation later on in the last part of your solution. Okay, it's very clear, no? I need to teach you usually for this because our next problem solving, it deals with chemical reactions. Okay, not only the purely mixing like that. Okay, we deal with chemical changes. Okay, the changes of matter, by the way, physical change and chemical change. Okay, get the point. O, diba? Okay, ganon. So, now, we will have two formula of heat now. Okay, we have Q is equals to mCp delta T. And we have also Q is equals to, take note, NCp delta T. So how can you use the two? Okay. This equation 1, if the given is in mass. Number 2 is in given is in the number of moles. There's no mass. We sometimes always like that. 2 moles of iron reacted with water like that. Calculate the heat of iron. Now it's not the mass usually. Okay? So you will use number 2 equation, the NCPDT. That's why there are other versions of Q. Not always that NCPDT. Originally, timanan, until ka mo graduate. No, it's not. There's also NCPDT. Number of moles times specific heat capacity times delta T. But take note, after your answer, okay, you use the molecular weight for this. Okay, you get the point? Your purpose of using the molecular weight, because sometimes the choices will be in grams. And you don't have grams here in your second equation. For example, the original problem is given the 2 moles of blah blah blah, then ask for the grams later on. Okay, that's the benefit or the faida of using the molecular weight. Because it mentioned on the number of a gram per mole. Like that. So you will cancel directly the mole here. See? Mole here. The gram kabilin. Diba? Ganon. Okay. Any questions so far mga palangga? Nothing, right? Okay, that's very clear. I hope you like this explanation and you can comment down below the comment section and then you can subscribe if you want my YT channel and I will be very ecstatic if you can do that for me. Thank you. Bye-bye. God bless everybody. Remember that Jesus loves us. See you later in my next vlog and next problem solving. Bye-bye. Talaga. Pagkain. Hello guys, Charis.